Hi everybody, welcome to this video about routing multiple point-to-point problems. Some work I've done with Rijts Jansen, Yannick Finkelstein and myself of course. And it's accompanying a paper which has been published at Gecko 2020 in the workshop for permutational problems. So first of all, to give you a little bit of context, a point-to-point routing is a problem in which several paths should be routed from one point to another, but should not collide. So a very clear example of this is in the middle, right here, pipe routing on ships, especially in engine rooms, where you have a lot of pipes which should be routed from point A to point B, but should not collide with any other pipes, so they should move up or down or whatever. Similar problems arise in neuromorphic systems, in chip design, very important, but also in robot control, for instance in warehouses, where many robots move simultaneously, but of course they should not be at the same point at the same time. Now, and the quote down here is very important. It comes from a book by Konstantin Moiseev and co-authors, and it basically states that one of the critical factors of these problems being very hard is that the order of handling these problems might cause one route to be blocked for another, right? And Konstantin Moiseev's book is originally from chip design. So we have a little toy problem here that looks a little bit like that, but it could be robot control, it could be pipe routing on a ship, it could be whatever. We have a little mesh here with 6 terminal points, and we have some paths from terminal 2 to terminal 3, 0 to 1, and 5 to 4 that should be routed. And then we start the process. And first of all, we route this connection over here, but then we see that the second one from T0 to T1 cannot be routed without causing a collision. Cannot be routed. There's no solution to this problem. But look at this trick. There we go. If we now start with the path from 0 to 1, and then with the path from 2 to 3 and the other one, all of a sudden, the unsolvable problem becomes problem instance becomes solvable. And we think that this is exactly what Konstantin Moiseev meant by his quote in his well-recommended, I should say, well-recommended book about chip design. Right? So this led us to the following questions. Obviously, if you have meshes, the more paths you try to route, the more crowded it gets, the more unsolvable your problem instance is likely to be, right? So how does this routability, the ability to solve your routing problem, depend on the path list length, the number of paths you're trying to route? How does it depend on the mesh size? Because as the room grows bigger, of course, you can route more easily. And how does this permutation, the changing of orders in the list, affect the solvability of the problem? So therefore, we designed an experiment with 9 meshes, which have a base plate, you can see bottom right here, of 20 by 20, 30 by 30, 40 by 40, up to 100 by 100 grid points. Yes, we strew 100 randomly distributed terminals on the mesh, just throw them on there, and then we have 7 upper layers so that the paths can also move up and down, like in piping, like in drone control, like in neuromorphic systems, and even like in chip design. For each of these 9 meshes, we have 20 path lists varying from 10 to 11, 12, 13, 14, etc. Paths to be routed within that mesh. And this accounts for a total of 14,500 roughly. And then we start routing these lists. So all the paths in the list get routed. And they get routed with an A-star algorithm. And A-star is a very famous algorithm. It's a very good algorithm. It's very much like the algorithm written by the Dutchman Dijkstra. It's a little more advanced, and it's complete and optimal. And that is very important, because the fact that A star is complete means it always finds a path between two terminals if it exists. The fact that it is optimal also guarantees that not only it finds a path, but it also finds the shortest path, or one of the shortest paths, if it exists. And this is very important, because that means that A star does not cause any paths in the mesh to take up unnecessary space. It makes them as short as possible, and it's guaranteed to find a solution if there is one. So after routing these paths, we changed the order, we permuted the path list, we changed the order, and we looked at the effect of that. Okay, so let's look at the length first. So what we see here, and this is just a result for the 60 by 60 mesh, remember we had 9 meshes, this is just a 60 by 60 mesh, is that the longer the number of paths gets, the longer the path list gets, the less likely it is to contain a solution, right? And we can characterize this, the dots here is the fraction of 20 path lists that's routable, and the length is of course on the horizontal axis. Remember, for every number here there's 20 lists, so right about here, this point here, about that's 35, about 10 lists are routable. 10 out of 20, right? So this is the fraction of routability. And this probability, if you like, this routability, behaves a little bit sigmoidally, if you like. It has a S kind of curve in it. And for characterization, and we'll see why that is important later, we use this function over here, which fits really, really nicely to the data. And L in there is the horizontal, is the number of paths. H is the horizontal shift of the graph, and S is the slope, the steepness on the routability point. Now, what is the routability point? And we need this point because we need some point to define the entire graph. It is the point where about 50% of the paths of a certain length are routable. So for 60 by 60 mesh containing 35 paths, within the random terminals, the chances are that if you have 35 paths randomly distributed, chances are about 50% that your list is routable, contains a solution. So we've done this for all the mesh areas, different meshes, and what you can see, and this is quite obvious of course, is that the routability point, the 50% routability point, shifts to the right. So as meshes get bigger, you can route more paths. And this is understandable because there's more room. So they're less likely to collide, right? And less likely to clog and to become intertwined in a kind of stuck spaghetti, as you can see up here. So the routability point shifts to the right, which indicates that more paths can be routed in larger meshes. This is kind of understandable, but we also have a characterization for that. And you can see that bottom left here, and it's a logarithmic function. And this is really the power of the work, because a characterization like this allows us to predict, even for very, very large meshes, and even for very, very large path lists, which happens in chip building, for instance, or in very large ships, or in buildings, or in chemical plants, allows us to predict whether, a priori, even without doing the routing process itself, we can predict whether it will contain a solution or not, at least to some extent, because it's not extremely precise, of course, but to some extent, we can predict for very large meshes and very large path lists whether they are routable or not. That's the strength of this work. But there's more. So after this, we did the exact same experiment, but we took all the original net lists, path lists, and we permuted them. We just randomly changed the order, completely randomly. 200 times for every path list. That amounted in about 3 million path lists to be routed, so there was quite some calculation and quite some data, but that's good for the rigorousness of our results. If one of these 200 permutations actually contained a solution, so it might have turned an unsolvable path list into a solvable path list, as you saw in the toy problem in the beginning. And you can see the results right here in these orange dots. In my eyes, they are red. I'm slightly colorblind, so sad. But they also form this sigmoidal shape, and it becomes much, much higher than the original shape. So basically, the takeaway message here is that if you have some length of path lists with a certain routability, that the chances are that if you are allowed to change the order in some way, in some random way, 200 times, that your unsolvable problem instances might suddenly become solvable. And this is the second very strong result, I think, of this investigation. And the new solvability sigmoid can also be characterized by the inverted logistic function. And again, we have the original routability point, and we have kind of the permuted routability point. The routability point you get assuming that you are allowed to try 200 different orders in your path lists. And the difference between those two, and you can see it right here in this figure, but also right here, is very, very tight. And the results are very, very clear, is that for the parameters that we have used in this investigation, that 200 permutations allow path lists of 73%, that's a huge, huge number, 73% more paths to be routed. So if at some point you have 100 paths which have a 50% routability, if you can change the order of paths 200 times, just make 200 new path links of the same list, then all of a sudden you can route not 100 paths, but 173 paths. And that's, of course, a huge, huge difference. So there are a few open issues left. First of all, it should be noted that these kind of sigmoidal transitions, as we see them here, are very common in NP-complete problems. Right? In satisfiability, in Hamiltonian cycle problem, they are very common. Now for 2D routing, it has been proven, this is very closely related, that it is NP-complete. By our knowledge, the 3D routing, we are not so sure. So the sigmoids themselves are not so very surprising, but the connection should really be investigated for the sake of theory. But there are a few other points of attention. First of all is these 200 permutations, which make unsolvable instances solvable. What characterizes the good permutations? In what order should we route these paths to obtain solvability from unsolvability? Should we route the shortest paths first, or the longest, or the terminals which are in the same latitude? We don't know. We're still dying to find out. Second, of course, our 73% depends on the number of permutations, in our case 200. What if we do more? We are likely to obtain higher results. If we do fewer, we are likely to obtain lower results. And what is the exact influence of the number of permutations on the routability? We still need to find out. So before I'm out, a few acknowledgements. First of all, Sara Bulfon from STI Engineering, Design and Consulting. I think she's from Trieste in Italy, who supplied us the pipe routability image. And then Kees van Leeuwen, a professor from Leuven, and Pieter Adriaans, a professor from Amsterdam, University of Amsterdam, who helped us do some reviews. Very much, thank you very much. And then the reviewers at Gecko, who really did an awesome job. If you have questions, drop me a line, drop me a comment, and I'll see if I can get back to you. Thank you. Bye-bye.